My name is Angel Kagemovic, and I'm a PhD candidate in English Language and Literature at the Faculty of Philosophy, University of Novi Sad. And today I will be the moderator of this e-conference on the topic of affordable and clean energy. So this e-conference is a part of an ongoing series organized by the EUGLOH Alliance, focused on the UN Sustainable Development Goals. For this edition, the Lund University and Paris-Saclay decided to co-host a conference dedicated to exploring Goal 7 of the United Nations 17 Sustainable Development Goals, and that is affordable and clean energy. In short, goal number 7 is dedicated to ensuring access to affordable, reliable, sustainable, and modern technology and energy for all. It focuses on increasing the use of renewable energy sources, improving energy efficiency, and expanding infrastructure to ensure clean energy and to ensure that it is that everybody globally has access to it. Achieving this goal is crucial for reducing greenhouse gas emissions, combating climate change, while also promoting economic growth and improving living standards in underserved communities. Today, we're bringing together experts from University Paris-Saclay, Professor Benoît Gabrielle and Professor Bruno Darrac. But prior to that, we will hear from the Lund University and its students. We will hear from Martin and their insightful Solstice project. As an attendee, you will receive valuable insight in the topic, and you will also get to engage through Q&A sessions. In addition, you will have time and space to exchange with our speakers at the end of the conference. So I'm going to introduce our first speaker, Martin, the student from, as I said, Lund University, and he will present the Solstice project, which is an innovative approach to solar energy storage, and it tackles one of the key challenges in the development of green energy solutions. Martin, the floor is yours.
Thank you so much. First off, can you all see my screen?
Yes.
Great. My name is Martin. I'm a recent student at Lund University, and I am the CEO and founder of Solstice. We can stop climate change today and bring affordable and renewable energy to everyone, but are choosing not to because it's too expensive. Thanks to innovative breakthroughs, wind and solar are today the two cheapest forms of energy, and that's incredible. But we're still left with a huge problem. Every night the sun sets, and 60% of the time the wind doesn't blow. Our only renewable solution to this is hydropower, but 50% of the world's hydropower is limited to just 4 countries. And everyone else need to rely on energy storage. But storage is extremely expensive because batteries are toxic, rely on rare earth minerals, and are very limited in their use. Today, they cost more than 4,000 crowns per kilowatt hour. And for all of those who don't know the Swedish currency exchange, 4,000 crowns is roughly $400 or 400 euros. And this is a huge problem, which sheds light on the scale of the problem at hand, keeping us to this day dependent to have fossil solutions to take over when the cheap renewables fall short. But we have a solution. We can lower the cost of storage with 89% by using the cheap medium of sand. Not only solving the intermittency problem of renewable energy, but also keeping it accessible and affordable for everyone. Today, more than 3.5 billion people lack access to stable electricity grids, and 700 million people lack access to electricity at all. And these 3.5 billion people, they have electricity in the form of solar panels where they get access to charge their phones and so on. But they don't have a stable grid and they have rolling blackouts. And this is because it's very hard and expensive to have a stable energy grid. And this is because there's no simple silver bullet. When you have wind, you need to balance it with other sources. When you have solar, the same. And it's a balance dancing game, which makes it so hard and expensive. So how can we lower this cost of storage? By using the two most abundant resources, heat, solar heat, and sand. With this collector, as you can see on the screen, which is a giant mirror, we collect the heat from the sun, and then we transfer this heat to a sand battery, where we can store it for days or months, and we can create electricity and district heating from it whenever we wish. And with this, we're not only providing energy, but we're also providing energy on demand, which is the baseline for a stable grid. So this is a silver bullet to providing its own microgrid, which means you don't need any other power sources to balance it for keeping a stable grid. And this might seem like a lot of new things, but we're actually using two existing solutions. These solar mirrors were very popular in the 80s, where they hoped to compete with solar panels. We usually use mirror to create electricity. But due to the drop in prices of solar panels, they were uncompetitive and sort of forgotten, but they were extremely efficient at producing energy. And these sand batteries are as simple as they sound. It's basically a silo filled with sand that you just with electricity. And since sand is very available and it's just a silo, it's very cheap to store large amounts of energy. But since you charge it using electricity, it's extremely wasteful and inefficient. And thus, these two technologies are uncompetitive on their own. So what has changed? We have found a way to connect these two. This red line is our transfer device and our innovation, which we came up with as students in Lund. And we just thought this should work. And we went to a professor and we asked him, we think this should work. We read some studies and this phenomenon works in this application and this applications, but it hasn't been widely used. Can we try it in this new application? And he said, yeah. And then we found another researcher and we asked to use the solar lab at Lund University to conduct our experiments. And the third part in this, we asked the incubator at the Lund University for funding to do our experiments. So with these three parts, we set up our own experiments during the summer months in the solar lab, and we actually validated this technology and transferred 71% of the collected solar heat to a very small scale battery. And with this, we can connect the two technologies. And not only that, we actually get both the benefits, the high efficiency of the solar mirror and the low cost of the energy storage, but we don't get the drawbacks because these solar collectors, the reason why they were uncompetitive were because they were so large, because they had an engine on top of them. But with our technology, we don't need the engine and we can thus make them very small and thus also very cheap. And this sand battery that is very cheap to build is very expensive and inefficient to charge using electricity. but we're charging it with abundant heat from the sun, which makes we get both the benefits and none of the drawbacks. And with this, we have done some market research on the Swedish energy market. And the levelized cost of energy is 0.27 crowns, which is, to put that in perspective, is roughly the same as wind energy in Sweden. And since this also has energy storage and can power up on demand, you can also add it to the frequency balancing market, stabilizing already unstabilized grids. So this is not only a microgrid solution, this also helps to use more wind and solar in already established grids by balancing the grid itself. And the waste product of the whole system is a lot of waste heat, perfect to use for district heating. So we have validated this technology inside the lab in Lund University. And we also conducted a lot of market research where we spoke with a lot of energy companies around Sweden, because we thought the best ways to use this is to use all the energy you can, and that is both electricity and district heating. And there we actually found a niche market. Like in Sweden, it's not famous for its solar energy, but we found that in the summer months, district heating use is so low in Sweden that the energy companies can't scale down their production. So they can't provide the little heat that is needed. So to cope with this, they have a backup generator that's run on very expensive biofuels that's also very limited and could be useful in other purposes. And this is very expensive for the energy companies, and they're using biofuel that is better used in other settings. And this is only for the summer months. So when we spoke to the energy companies about our idea, they said, this would be perfect because this only works in the summer months, and that's the only time when we have this problem. And with that said, if we can make solar power work in the cloudy, rainy, cold Sweden, you can make it work anywhere. And not only that, in sunny countries like the Mediterranean and Middle East, this is not only a summer solution. This could be the balancing baseline of an energy grid when it can work all year round, making the potential so much greater, even if you can't use the waste heat in district heating. Only the benefit of cheap, on-demand solar electricity is a game changer. So we started this journey last year when this just popped up as an idea, and we spoke with some professors, did some experiments, and my friend also made his thesis on the subject itself. And since then, we have received numerous grants from private and public scholarships, and we also raised some money. And right now, we're actually building our first complete prototype in the workshop in Lund. And not only that, we have also initiated our first pilot project with an energy company called Bioenergy, short for VIAB. And this energy company is having this specific summer months problem with their energy production. And they're thrilled to be part of our journey, and we hope to build a full-scale pilot project in the coming 2 years. So this is not only for Sweden, but also for the world, and it could be both for industries and home application, and especially microgrids, because a large hurdle in developing countries is not that there is no energy grid or energy, but that it's very expensive to build out the energy grid to a destination to provide the power. In this setting, it would be much cheaper to open a new microgrid, which this solution allows to lower the cost for. So I'm of course not doing this alone. I have my friend Hampus Hammarbeck, who is a mechanical engineer me myself is an electrical engineer, and we also have Malin Eriksson, who is a master in business and innovation. And the professor who allowed us to do all this in the university property is Lei Wang, and is our senior advisor. And we are all working with this tirelessly to make this happen. So please follow our journey by scanning this QR code if you are curious, have questions, or want to be part of it in any way. Don't hesitate to contact us. We don't have a flashy website or any of that at the moment. Most of our time is just working in the lab, getting this thing to market as fast as we can. Thank you.
Congratulations, Martin. This was really, really, really interesting and extremely useful, as everybody can see and observe. And it was a very compelling presentation because it caught interest right from the start, and even for basically a newbie in this topic like I am, I think it's very well explained, and therefore everybody can actually see how relevant this topic is. Now I would like to ask the audience to pose several questions to Martin, because he will be with us for another 10 minutes or so. We already have a few questions. Actually, we have super interesting, so congratulations. That comes from another Martin. And we have a question from Kari. She asks, what do you mean by grid? And what kind of sand mixture do you intend to use for the storage?
Yes, so grid, is the energy grid. So like all the power lines and all of that, which could be the national grid that also connected to all of Europe in Sweden's case, but it could also be a disconnected microgrid that's just a village in a developing country. And for the sand mixture.
Mm-hmm.
Yes, so if you are inside the construction industry, you might know that it's a huge lack of sand. And that might be hard to know if you look at the Sahara Desert, but that's because they use a specific sand that's used in rivers and so on, and it's very limited in all of the world. But the great thing here is we can use almost any sand. It just needs to be cleaned and processed, and then we can use all the sand in the Sahara or in your backyard or wherever this might be.
Brilliant, brilliant, really. We have another question from Isabel. She asks, how much cost to build all the infrastructure? Thinking in making dozens of it? Yeah, so how much would it be to build all the infrastructure?
So not comparing this to like a wind park and so on, so not the power lines and so on. The storage cost is 10% of what a battery system would cost. So that's $45 per kilowatt hour of storage, so to say. And the energy producing cost is around $1,000 per kilowatt. And to put that in perspective, solar panel today cost around $900 per kilowatt. So it's slightly more expensive than solar panels when just producing electricity, but the storage cost is significantly lower.
Okay. We have another question. So we have the point that storage energy is a challenging process. And what would be the uniqueness and the, let's say, why does your solution seem so unique in comparison to the others? And whether you are aware of the work of the company called Azilio, and whether and how is your solution different?
Yes. I'm well aware of Acilio. I'm not sure if they are still operating, but they are using a similar technology. They are storing solar heat inside aluminium. And this is a great idea. Just like salt storage, which you might know in Spain, they have these huge towers with lots of mirrors where they store solar heat in salt. And these two systems have many of the same benefits as we do. But they have one huge drawback in both cases. And that is both that salt is extremely corrosive, and also aluminium is also very corrosive when you change it in phases. So this system perform very well on the benefit side, but they also have huge maintenance issues and downtime due to all of this corrosion, which makes them quite expensive to operate and need a lot of expertise people to constantly monitoring them, which is not the case when you just warm up some sand.
Okay, makes sense. Okay, there are a lot of questions for you. I will continue. Get ready. Another question says, since your invention is likely patented, could you please go into physical details about the red link? That's the core of your idea, and I really have a hard time figuring the concept that makes it so efficient.
So it's actually a patent process, so I can't actually go into the details. Hence, it's a red magic box. But the reason why it's so efficient is because there's different kinds of heat. You have the worst heat that's very useless. That's around 40 degrees. You can't do much except maybe heat something with it. And then you have the top quality heat around 1,200 degrees. That you can not only make electricity, you can use this in a huge amount of industrial processes as well. And for all of these processes, you're mostly burning coal and oil today. And what we have done is you can, of course, just heat some water with a mirror, and you can get maybe 90% of that energy to a sand battery. But what we have done is a quite complex solution, which makes that even though we're a quite small mirror, we can get huge amount of temperatures on a small scale. And we can convey this huge amount of high quality heat to the battery. And this is the innovative part, which means that we can get not only an efficient, but also high quality, high temperature heat from a solar mirror inside the battery, which gives a high quality, wide use product in a cheap way.
Okay. The next question says, what are some of the key challenges the project faces and how are they being addressed?
So being completely honest, one of the biggest challenges is a thing called bankability. And that is to make, here we have a lot of innovative parts and not widely used, even though the sand battery and the solar mirror existing technologies, you don't see them all over the place everywhere. And presenting this to a bank, they might say, oh, what's this? I don't know. We're not going to lend you money for this. If you want to open a solar park, you get all the money you want. But even though this would perform better, the bank is very scared with its money. So we need to prove the technology and prove that it not only works, but it works very well, and the bank will get its money back. And it's a very capital intense industry. So it's not, I used my pocket money to build and do this. It's cost hundreds of thousands of kroners and dollars to not only build this, but also connect it to the grid and show that it works. And that is both bureaucratic, capital intensive, and sadly quite long project, which we are in the middle of. But that is, it's harder than making an app, so to say.
Obviously, yes. Okay. Okay. I understand and definitely do all the others. I suppose you will have to leave now. So I will have to disappoint all the other people who asked questions, but maybe our other panelists will be able to answer their questions later at the end of the QA session and this whole session. Thank you, Martin, for this marvelous presentation, and I hope that your project will see the light of the day very, very soon.
Thank you so much. It was my pleasure.
Yes. Okay. It's my honor to introduce our next distinguished speaker, Professor Benoît Gabrielle, Vice-Rector for Sustainable Development and Societal Responsibility, and Professor of Bioeconomy and Sustainable Science at AgroParisTech, University Paris-Saclay. Professor Gabrielle's extensive background includes a PhD focused on the environmental balance of oilseed rape for biodiesel production, followed by his tenure with the French National Institute for Agricultural Research. His affiliation with a research unit dedicated to the functional ecology of agro-ecosystems has allowed him to contribute significantly to advancing sustainable agricultural practices. His research interests span a wide range, including the biophysical modeling of agro-ecosystems, environmental assessments and energy crops, and of course, sustainability analysis of bioenergy chains. Today, he will be presenting on the topic Bioenergy, a clean and affordable player in the energy transition. Please join me in welcoming Professor Benoît Gabrielle as he shares his insights into the role of bioenergy in achieving a sustainable and affordable energy future. The floor is yours, Professor.
Thank you, Angelica, for this nice introduction, and good afternoon to you all. Thank you for joining. It's exciting for me to share this, your thoughts and perspectives about bioenergy. So we're shifting away from the usual renewables we've just heard about, wind, solar, and geothermal, etc., which pose the issues that Martin raised. And actually, bioenergy is also a way to store energy. But of course, there's a key question there about its sustainability. And as you understood from my previous work, this is what I intend to contribute today in this seminar. So basically, yes, I would like to introduce bioenergy to you and actually ask you a few questions. You'll get to participate even before the Q&A. And most of what we can expect from bioenergy, I think, is determined by its sustainability. And this will be the core focus on this talk as per its title. So I hope to shed some light there and, of course, foster some thoughts about the role that bioenergy can play in the future. And I would like to then continue and wrap up by positioning bioenergy in the wider approach to, say, paradigm of bioeconomy. And that's maybe a channel for a sustainable future. Okay, so I would offer you to contribute what you think, what comes to your mind when you hear about bioenergy. So if you have a phone or let's say browser accessible, you can enter wooclub.com and then the code, which is SCPFGH. And I just started there will be 2 questions to sort of engage you and start engaging with the topic. So I'd be curious to hear, or actually to read what comes to your mind when we talk about bioenergy. So I've just started the question, and maybe I'll leave a few seconds here for you to start contributing. And then, oops, sorry, I didn't share my screen actually. So here we go.
Yes. Okay. Now, yes.
Yes. Now you can see the poll. Sorry about that. I was too engaged with anyway, the first slide was just the introduction, so you didn't need the slide to go. So yeah, if you would like to contribute and tell me what you think about bioenergy, what you know, and I'll leave a few more seconds before I start diving into what do we mean by bioenergy, what can it produce, what it is in practice, and then go into sustainability. So I hope by now you can access the poll. And I won't share the screen because I've had trouble sharing my first screen. But anyway, I will just report to you orally what you're writing. So some of you wrote sustainable, which is interesting. Biodiesel, biofuel, heat, movement, natural. Okay, energy, of course. Okay, great. Okay, you can keep answering, and then I will continue with the presentation. So yeah, bioenergy, as you wrote. Oops, sorry. I shouldn't shift the question though. So bioenergy is basically energy derived from biomass. So resulting from a photosynthesis. So I guess you all know what this is, but I'll come back to the biomass recipe in a few slides. Anyway, so the uptake of CO2 from the atmosphere by crops to produce organic matter, and which is found in crops. So like this sunflower field in Italy by trees. This is a giant sequoia. It's probably not used for biomass production, but anyway, it's the iconic example of a tree and forest. You can also find it in forest residues and agricultural residues. So you see a pile of wood chips on the right of the slide, which has been processed from branches after, let's say, clearing a patch of forest. You can also find it in a lot of different organic waste streams from livestock farming. So this would be farmyard manure, for instance, from food processing, wastewater treatment, and you see a wastewater treatment pond, more or less. So that's the sludge that comes out of it is biomass. And the last one is biomass that grows in water, which is called aquatic biomass. So algae, microalgae to your right, to the right of the slide at the bottom right-hand corner, and it can be also seaweed that grows on the seafloor. So all this is biomass, and it is important that it's a recent photosynthesis process involved behind it, because otherwise you could consider fossil resources, which also evolved from photosynthesis as renewable, but it's not renewable because this is photosynthesis from millions of years ago. So now this is a complicated slide, just to say that from biomass you can connect a lot of conversion processes and leading to different end uses, which you mentioned in the poll. So biofuels, you mentioned heat and think, and mechanical power, which would be biofuels used for transport, for instance. We can also produce heat and cooling, energy carriers like electricity, we just heard about, or hydrogen. So basically, with this biomass, you can do a lot of things, and the schematic here shows how it can be organized into a value chain. So from a feedstock source on top to an end use at the bottom, and then in the middle, you have these conversion processes, which can be physical, chemical, or biological. And for instance, thermochemistry, so the left arrow involves cooking biomass, basically. So sort of breaking down the organic matter into simpler molecules, and you can obtain hydrogen from that, for instance, or CO, and you can recombine CO and H2 to produce biofuel. So you can do a lot of things with thermochemistry, and when you actually build a fire in your chimney, in your fireplace, that's thermochemistry, very basic heat production. You can do also, some of the processes are very specific in terms of biomass they can take in. For instance, to produce biodiesel, which was already mentioned, you need an oil crop, so it can be sunflower or sea grape or palm oil, and then you will go through this chemical process of esterification with an alcohol. So you need a food crop, and that's obviously the first imitation of these biofuels, which are not so popular these days. And we prefer advanced biofuels, which can be obtained through thermochemistry or fermentation of any type of biomass by yeast to produce ethanol. And the last process to the right is the digestion of organic waste, which can produce biogas, a mixture of methane and CO2. And you can use that as a substitute for natural gas to produce heat or power or even fuels. So a really multifaceted, let's say, realm of applications. And that's, I think, the beauty of bioenergy. And then the last one is algae, which you can use for biofuels, for instance, or fermentation. So in practice, now we're shifting to less complex slides. This is to the left, a power station in Spain, in Miajadas, which produces electricity from crops and trees. And the capacity is 16 megawatts. So it's not so large, but for a biomass plant, it is. It processes about 100,000 tons per year of biomass. And on the right-hand side, you see an example from India, where this lady is standing in front of a small-scale digester producing biogas from typically cow dung or food scraps, agricultural waste. And this is actually a very interesting alternative to what is called the traditional biomass, which is actually the first source of energy in some countries, and actually also the major source was in terms of bioenergy in general. So biomass has been around for many, many years. As you probably know, it was the first source of energy ever harnessed by humanity. And here you see that when you use it to cook in an open earth sort of fire, it is very inefficient, and it can also cause health problems. So it's particularly, I think, relevant to us as EUGLOH, because we're touching on health here. And biomass in this kind of configuration is actually dangerous because it can harm people, from the low quality air inside this house. So there are many incentives to shift to modern forms of biomass, which are more refined, more sophisticated. So the kind of arrows I was just showing before, to also reduce the pressure on the local biomass resources and the forests, for instance. The same goes for the this low-tech, I would say, traditional charcoal production to the left. I'm not sure where it is, probably in Brazil or something like that. So anyway, this consumes a lot of biomass and is not very efficient. So this is the sort of traditional versus modern divide. Of course, when you talk about developing bioenergy, we probably want to develop the modern one, but traditional biomass, as it's called, accounts for about 7% of the overall use of energy in the world. This is the breakdown of energy, final energy consumption worldwide. So you see the role of traditional biomass is really emphasized here. And you see modern biomass in the right-hand side with biofuels or other types of bioenergy chains, which is smaller, actually, in fact, but could be developed in the future. And that's kind of showing the place of bioenergy. So bioenergy is an important, of course, player there in terms of contributing to the share of renewable energy in our overall consumption. The others are on the rise, I should say, but so is bioenergy. So overall, renewable energy contributes about 15%, and bioenergy about 10% in that 15% chunk. So now I'm moving to sustainability. And so I'm opening a second question, if you want to go back to the poll, about what are the issues you see around sustainability? So I'll let you start answering, and for the sake of time, I'll just continue with the slides here. Just to explain what are the stakes for sustainability in biomass. So basically, to produce biomass, you can use the equation of life, so CHO and PS. And so you need carbon, which comes freely from the atmosphere. There's actually too much of it. And that's an opportunity actually for biomass there to play a role. You need water, which is available but limited in some areas, and that provides the hydrogen. And then you need nitrogen and phosphorus, which usually comes as fertilizers to crops. And these are the major nutrients limiting the growth of crops worldwide. And also, of course, you need land to produce crops or trees. And that's, of course, having said that, you see that producing more biomass to fuel the bioenergy will actually impact a lot of what is called the planetary boundaries. I'm sure you know about that framework. A political, let's say, translation would be the Sustainable Development Goals that Angelica emphasized in the beginning. And when you when you connect these boundaries to environmental boundaries, let's say, to bioenergy, you see that, of course, land use is impacted by bioenergy. We might need more land, but it's limited, and we're in the gray, yellow area zone for that boundary. We need water, we need phosphorus and nitrogen, and these cycles of these elements are already disturbed, maybe past some irreversible threshold, where you also might impact biodiversity. And climate change, and we should strive actually to make a positive contribution to combating climate change. So you see there are many issues at stake here, and it's not easy to keep within that safe or operating space when developing biomass. So now in terms of land use, this is a picture I usually show with a lot of caution because it's a very simplistic, oversimplified view of our land system. So we have 13 billion hectares of terrestrial land, ice-free land on the planet. 1.5 of those are used to produce food. And for bioenergy, it's something between 13 and 60 million. So it seems that it's a tiny dent in our land use, in our land system. And this report proposed to increase the energy production to 100 and 200 exajoules from currently around 60. So doubling or trebling the output would not apparently encroach too much on our land area. Of course, this is a simplistic view because not all pieces of land on the planet are equal. Some of them are cold or too warm to produce biomass, etc. So it's just a word of caution, but that's the way to visualize this. I think, I don't have that much time left. So I would like to talk briefly about another factor that is connected to the boundaries, is the fact that with bioenergy, you can withdraw CO2 from the atmosphere. That's called bioenergy with carbon capture and storage. And you see the technological system here. So you use photosynthesis, produce biomass. You use the biomass to produce energy, different source of energy. Nothing specific here. And then you scrub the CO2 out of the flue gas coming out of your combustion process, for instance, and you store that in some reservoir. And so basically that's a way to pump CO2 out of the atmosphere. So it's a negative emission technology. And in the IPCC report on how to keep the global warming under 1.5 degree, you'll see in the different scenarios that they used a lot of that option. It's called BECCS, BECCS for short, and that's the orange part of the negative emissions there. You see on the different graphs, your projections to 2100. And also, if you go behind these sinks of CO2, so to speak, you see that a lot of land is involved, up to 700 million hectares. So that's really more than a dent in our land system. And that's probably not sustainable. And actually that was pointed out by another report, but I just really run through this on climate change and land in 2019. The report said, we don't want to do large scale deployment that we would jeopardize food security, the red bar on top, that would be too costly. So we're coming to the affordable point here. And we want to do bioenergy right. So putting all these issues into the green zone in terms of adapting to climate change, reducing desertification and land degradation, and not infringing too much on food security. And they went to a lower, let's say, deployment ratio, but yeah, okay, I have to stop because I'm already over 16 minutes. Okay, well, bioenergy can be done right, and I'll skip the bioeconomy transition. That's for the discussion. So anyway, bioenergy will be needed in the transition to clean energy systems, and within stringent sustainability limits. It can also offset CO2 emissions, and so there's a lot of hope here in the different scenarios. We'll see if it materializes. And it can be placed under this transition to an economy running on biological resources rather than fossil ones, and also to the global health agenda. And the last take-home message, of course, also very much a matter of economics, public policies, and governance. So I will leave it there. Thank you for your attention, and sorry if I took too much time. And thank you also for contributing to the questions. I see. I'll comment your answers in the discussion. So back to, thank you very much again, and back to you, Angelica.
Okay, yes, I'm here. No worries for the time. It was really highly informative, for me, very thought-provoking. And also it encouraged us to consider some new perspectives. So it was definitely a very valuable insight. So once again, I will let the audience ask questions in the group chat. And if, in case we don't have time to answer all of them right away, we can discuss them later in the Q&A session. So we're waiting for the questions. Okay, here it comes. It says, thank you for the presentation, super interesting. I have one question. How does the economic viability of bioenergy compare with other forms of renewable energy?
Yes, a good one. I didn't touch on it too much, although I advertised affordable. Well, given the scale of its use, you could say that bioenergy is competitive, but as I said in the end, it's also a matter, especially for the traditional form, that's the cheapest and most easily available source of energy for a lot of people. But in general, as I said in the end, it depends on policies. And for instance, the Miajadas power plant I showed, they're still in business, but they're not using crops anymore because the government stopped subsidizing energy crops, basically, which were grown on rangeland. So it was not replacing food crops. It was more like they were being shared with cattle, I would say, cattle farming. So anyway, you see that there's policy interventions are really important. And also biogas, for instance, which is developing very rapidly in Europe. If you go to Germany, you'll see these digesters, this sort of plastic bubbles, more or less, next to farms. You'll see them everywhere. So this all happened because the government decided also to put a feed-in tariff for electricity. So let's say to buy electricity at a special price, and that made these digesters very competitive. So yes, in general, if you look at the new forms of bioenergy, this is also the case for biofuels, you have to subsidize them in the beginning, but then, like all renewables, they become competitive in the end. And the last point is that compared to the other renewables, bioelectricity used to be much cheaper. But around 10 years ago, the prices, the costs of solar panels, etc., well, especially if you source them from China, but anyway, dropped so much that it became cheaper to produce electricity with the other renewables. So there isn't maybe much to expect from bioenergy in terms of bioelectricity, I would say, but that really depends on local conditions, as Martin also pointed out.
Yes, well, it makes sense. Absolutely. Thank you. There is another question which says, what are some of the key challenges facing the bioenergy sector today?
Right. So we already mentioned the economics. And so again, policy support is probably key, at least in the beginning. Then, of course, the major limitation to bioenergy, that's kind of what I draw your attention to, is the availability of biomass and land. So you don't necessarily need more land to produce more bioenergy, because there's a lot of biomass produced by in residues, in waste streams. So, for instance, the digesters producing biogas, they usually use residues from agriculture or from the agro-food sector, etc. So that's a good source without having to devote more land to energy crops. But we will need these crops at some point, probably. And then we need to look at the land that's available without jeopardizing the production of food. And that's a real important issue. That's the one I'm working on these days with a PhD student. And so it seems that we could probably double the amount of biomass available within sustainability limits, I would say. But then there's a hard limit, something like that. So yeah, so there's still room for further deployment, but not maybe to the extent that, for instance, in the IPCC special report on renewable energy and climate, which I contributed to in around 2010, we were expecting much more out of biomass, and now it seems that probably the other renewables should weigh in heavily also in the transition. So yeah.
Okay. We have another question that asks if you could compare the other renewable sources of energy, and does it require more land or less for work at similar capacity?
Yes. So we can compare with the other renewables, at least the ones that I think you have in mind. So solar, PVs and solar panels, and wind. But remember, they produce electricity. And electricity, as Martin explained, faces a problem of intermittency and how you balance the grid, etc. Biomass is very interesting, and it was actually also mentioned by Martin because it's a form of energy. It's a storage of energy, if you wish, in the biomass. So it's like solar radiation stored in crops and trees in biomass. So in that way, it's complementary, I think, to the others, because again, it's not exactly like natural gas, but in a lot of we're talking about substituting natural gas these days. We could use biogas, for instance, or we could use biomass for heating. So it's not directly comparable. Again, for electricity, of course, if you want to produce electricity with solar panels or or wind, you will need a lot less land because the yield will be maybe 20 times higher with the solar panel compared to the crop one. So clearly, but actually, the trend is to combine both, which means you have solar panels in a field, and that's called agrivoltaism, and that's very popular because people don't know where to put the solar panels anymore. And so they're looking at land. So it's funny because we're looking for land for biomass and then for solar panels. So I think we could do both actually and combine them. But yeah, again, much more land for biomass by nature, but a different form of energy.
Okay, thank you. I just wanted to let the audience know that you can also write your questions in the chat if the Q&A doesn't allow you to pose more questions. So feel free to write your questions in the chat as well. Professor, for now, we will stop answering the questions, but please stay with us for the final Q&A session.
Sure, I'll be around. Thank you.
Thank you very much.
See you there.
Yes, thank you. And finally, our third speaker is Bruno, Professor Bruno Darrac, the Operational Director of the Center of Vocational Excellence, Sustainable Energy, which is supported by Paris-Saclay. He's also an applied physics professor, once again, Université Paris-Saclay, and today he will be speaking on the topic how to meet the need for jobs and skills in the field of sustainable energy. Reindustrializing France requires a focus on developing talent and investing in skills at all levels, whether the operators, technicians, engineers, or other roles. And therefore, their center aims to support the transition by adapting those diplomas into energy-related fields. Therefore, we will hear more of this in this wonderful presentation, and the floor is yours, Professor.
Thank you, Angelica. I will share my screen. This one. Okay, it's okay. Okay, so my talk won't be as technical as like the two previous one of Martin and Benoît, Gabrielle. Completely different, as you mentioned. My talk will be focused on the skill issues to meet the challenge of the energy transition. And just to begin, to remind you the urgency of the climate issues and also the importance of energy sovereignty. And in response to these issues, France has elaborated a roadmap called Low Carbon National Strategy, implying very large electrification of use, for example, for transport, heating. This electrification of use should be realized also by maintaining a large place to nuclear power and the energy mix, but also the development of renewable energies like photovoltaic, wind, and of course storage capacities with battery and hydrogen, which we'll discuss later in this talk. And finally, we need the electrical smart grid for smart management of the electrical network, transport and distribution. By improving the efficiency of energetic system and with an emphasis on sobriety, the objective also is to reduce our energy consumption and break out our dependence on fossil fuels, as you can see in this figure. So the energy transition implies some challenges described in this slide. First is to ensure the quality of initial and continuing training in energy transition professions. The second is to make technical profession more attractive, and so we have to promote the vocational careers. And the last is to create, of course, jobs in sectors of energy that experience a shortage for companies, including small, medium, and big companies. And so the organization I represent here is named Campus des Métiers et des Qualifications in French, and in English it could be translated in Center of Vocational Excellence. So focus on sustainable energy. This organization was created to address this challenge, as I said previously, by bringing and working together a different type of actors who are not always used to working together. These actors are of course training operators, technical training, vocational training, and secondary and higher in higher education, and also initial and continuing training. And other very important actors are companies of the sustainable energy sector. And of course, you know that in this sector, you have different kind of companies, small, medium, and big company. And another important actor is local, regional, national, and sometimes international authority or communities. And we are working also with research operators. I'm sorry, this picture is in French, but it's a summary what I said. And so, sorry. So just a few words about our organization, because the domain of sustainable energy is very wide. So we organize it in 4 thematic division and across functional axis. And so each division is managed by a small teams that include representative of training operators I mentioned, and so secondary and high school, university and engineering school, and as I mentioned, also companies of the each specific sector. So the sectors are described here, so the nuclear field, an electrical network, renewable energy, and energetic system. The cross-functional axis is focused on attractiveness, communication, inclusion, and health and safety prevention that is common that are common thematic in each division. And so our organization is funded by French government and regional council. So it's Île-de-France around the region around Paris. And also we are funded by responses to call for a project, can be a regional, national, international project. And in the next following slide, I will focus on a specific project we are leading now. And important is our organization is using or based on leveraging the physical and human resources of its partners. And of course, as it has been mentioned by Angelica, the organization is supported by Paris-Saclay University. And so this organization can give some answer to the, as I said in the beginning of my talk, the issue of skill development. In the following slides, I will focus on HTAS project. HTAS project is a project on hydrogen and batteries. This project is a five years project, 12 million euro funded, and consists so on the development, how to develop the skill on hydrogen and battery sectors. And different type of action are planned in this kind of project. So attractiveness, in particular towards secondary and high school. We have to develop training engineering to adapt curricula and also to train teachers. And so I will describe in the following slide what our methodology to adapt the curricula. And so this scope of this project is from high school to PhD, so very wide scope. And for example, in this project, so we will work with high school, target high school on the Île-de-France area. We will adapt formation, as I will show you just after, and also create or reinforce a technical center for practical works. And so we also will adapt diploma on bachelor degree with working with University Institute of Technology, and also on master degree. I will show you that we create new diploma, so it's another perspective, and we also manage some thesis on this area, on this field of hydrogen and battery. And so, just to be more concrete, because all that is very maybe very general, but so more concretely, the first work we have to do with our partners is to identify technical skills for working in the hydrogen or green, of course, green hydrogen sector. So that is the first step, and this must be done with training operators and industrial partners. So here you have the list of 4 critical skills we identified. So general information on hydrogen, for example, challenge facing the industry, and just we mention also the kind of job we can associate to these skills. So I won't describe all these skills, but there is, of course, for hydrogen, very important skills concerning safety and also hydrogen systems, production, storage, distribution, and you can see that these skills are to be given for specific jobs. Sorry for my English. And so also for this new domain, there is new standards, especially around European standards. So as you can see, the first step is to identify this new skill. And so when you have identified this skill, you have to adapt or create new diploma. And so this is our method to adapt existing diploma, which are not specialized on hydrogen, but by adding some training, you can make people operational on this domain. In this slide, you can see that there is different form of adaptation, from light adaptation, few hours, we call that coloration, light adaptation, or more bigger adaptation, and it will depend on the level. Here you have the level. So from back level, it's at the end of the high school. There is different specialization, not specific in hydrogen, but adding some training. You can make pupils or students operational on this domain, and so that is generic method we use in the other thematics. So first identify skills, and after how to see how to adapt existing diploma. It's more difficult to create new diploma and easier to adapt existing diploma. And so for higher level diploma, we create a new diploma. So the fifth level after baccalaureate, the master level, we created a new diploma, also based on the identification by industry of the future demand. And this diploma will, which is a high-level diploma, will cover the entire hydrogen value chain, so from production to safety, as I mentioned previously. There is also interdisciplinary focus on modules, and this diploma targets students trained in industrial engineering or other people already in work and wishing to retrain or specialize in the hydrogen sector. And so all this in this curriculum, there is a very big involvement of in our industrial partners. And this kind of diploma can be built with different universities. So we are supported by Paris-Saclay University, but the Campus des métiers et des qualifications is in the scope of the Île-de-France region, so can work and can make work together different university, in this case 6 university, so can mutualize the approach, and so that could be more efficient. So this is in the case of we have to create some deployments, but it's very rare that we have to do that. More often we try to adapt training, and so that I wanted to present to you. Maybe it's I don't know if it's okay for the time.
We should maybe try nearing the end.
Okay, so
we should maybe try wrapping up. Yes.
Okay, so it's okay for me.
Okay, then. Thank you. This is a very futuristic perspective. And I have to say from my own view that it's very useful, since in Serbia, for example, we don't train people for the jobs we will need in the future, and therefore we still train them for some rather obsolete positions. So this is a very, very useful and definitely worthwhile thing that you've been doing. Okay. Now I would like to ask participants, the audience, to ask several questions, either to Professor Bruno, or since now it's the QA session time, or to Professor Benoît Gabrielle. You can write in the QA session or in the chat. Okay, we have one for Professor Bruno Darrac. What are the next steps for this project, and how do you envision its long-term impact on the hydrogen sector in France?
It's a good question. The problem is this sector is not. We don't really know exactly what application of hydrogen. You know, it's there is some different application in industry, but it's not very clear. We know that hydrogen can be used for transport, for example, maybe more for heavy transport, maybe for hydrogen car, but it's not clear. There is also application on decarbonized steel. We know that also, but for the moment, it's a very this domain is not clear in terms of industrial perspectives, and so but we know that but it's important to have to develop skills on this domain, and maybe more high-level skills, engineering skills, research skills also, because we know that this domain is not completely mature, and so the perspective, there is there is companies that are big, that are created. So there is a perspective of jobs for small startup company, and now some bigger company. So we know that there is jobs after. So when we adapt training, we know that students or pupils that are doing this training will find job. So this is very important. It's also the case for the other thematics, electric network and renewable. We know that there is a lot of job, renewable energy, and also for nuclear. Nuclear is very important in France, and we know. But after the project, we support that what the engineering training we bring is allow the training to go further and to provide good students for the job.
Okay, thank you. Thank you very much. It's all definitely pretty clear that you're heading towards something that, as I said, is really relevant for the future of students, basically, and then therefore nationally and globally. There is another question for Professor Benoît Gabrielle, and it asks, what trends do you foresee in the bioenergy sector over the next decade?
Yeah, thank you. I actually saw that one on the chat, so I kind of was thinking about it. So hard to predict, as I said, 10 years on, after the IPCC report on renewable energy, I think the picture has completely changed. There's been an emphasis on carbon sinks and then hydrogen also, as Bruno mentioned, because you can also produce hydrogen from biomass, actually. But anyway, green hydrogen, that's a big issue these days. There's been agrivoltaics, so new technology sort of pushed, etc. But I would say that where we need biomass is probably, where there is a lot of expectations, is clearly in the transport sector, at least as an intermediate step between having all the cars or vehicles, even in trucks and maybe tractors, electrified. And right now, because we are still massively relying on fossil fuels. So that could be pending, of course, sustainability criteria, but there's a lot of work on that, I think, and policies. That can be an interesting avenue for developing biomass. The issue is that we've talked, I mean, I've been in this business, so to speak, for more than 20 years, and everybody said, in 5 years, we'll have, next generation fuels on the market. And it's actually 20 years on. They're starting to be on the market. But I think policymakers are not very supportive, I would say. So anyway, and the aviation sector is actually changing that, because they have short-term decarbonization targets, and the low-lying fruit for them is biodiesel. So they're scavenging any form of waste oil, from making French fries or whatever, to turn that into sustainable aviation fuels, are they called. And so there are many startups or bigger companies, Repsol in Spain, they're producing a lot of these biofuels. And they might be harnessing all the available biomass, and then what about the other uses? I'm not sure. So that's one thing, fuels. And then the biogas is also, as I mentioned, developing rapidly. So I think that's probably there. And then hydrogen, I think it's open, because one of the, if you want to produce green hydrogen, either there are many pathways, and I think Bruno knows much more than I do, but what I see from my window is that biomass is also a potential supplier. So there might be projects and expectations. The problem is, if you add up all the expected output from different sectors, it doesn't really match with the supply of biomass. So that's the big issue these days, even in around the low carbon pathway that Bruno mentioned when he opened his talk. It's supposed to be revised, and for political reasons, in France, internal to France. It's not yet out yet, but apparently one of the issues is what do we do with biomass? Because the aviation sector wants biomass, the transportation sector, terrestrial also, biogas, etc. So it's counted, 3 times in every plan. So yeah. So sorry, that was a long answer.
No, that was a very proper answer. Thank you. Okay. And there is another question for Professor Bruno Darrac. What challenges have you been facing in this project?
The big challenge is to make people working together. In fact, because there's very different communities. There is different communities. The communities of training operators. It's very large. It's secondary and high school operators. It's not the same as the universities or engineering schools. The difficulty is to make all these people working together. First, of course, industrial brings the needed. So this is very important. The starting point is industrial needed, and after there is the training communities and how to make them to work with industrials to construct this new curriculum or adaptation of existing curriculum, and so there is a lot of different people, and so this is quite very interesting because we learn a lot of things about all these communities, but this is the most challenging thing, I would say. But of course, it's a key point. If you cannot develop a formation without independently of needed industrial needed or some industrial perspectives. So and it's in France. It's not often easy to have an industrial inside the training or training establishment. As you know, it's not so easy. So this is a challenge.
Absolutely, yes, absolutely. Okay, now would be the time to wrap up this e-conference. And firstly, I would like to thank the audience for their participation and asking questions, as well as participating in Professors Benoît, Gabrielle's website thingy. That was, by the way, very, very cool and interactive method. So first of all, I would like to thank the audience. Secondly, I would like to thank our panelists for amazing presentations, as well as their commitment and dedication to this topic, which is obviously very, very relevant. And finally, I would like to thank Lund University and Paris-Saclay for co-hosting this conference. Thank you all, and I hope I will be seeing you again in some next session about some other very relevant topic. Thank you all.